Welcome everybody. My name is Pablo Arauzo, and I'm doing this study at the University of Hohenheim in Germany, Stuttgart, under the supervision of Professor Andrea Kruse. So today I'm going to talk about the valorization of poultry litter through wet torrefaction and different activation treatments. So today I'm going to show a short introduction, objectives, experiments, results, and conclusions. So why did this study take place? I mean, currently the poultry litter is one of the most problems for the treatment because it's composed by different things: manure, straw, feathers, feed residues, and the current use is like making the burning in the incineration. Because in the past it is allowed to use as fertilizer. However, currently with the European laws, this is not possible. We have to consider more or less it's produced around 150 tons of poultry litter in the world per year, because every chicken produces around 70 kilograms of poultry litter. So this in the past, coming with the idea, like in the past, the poultry litter was used like a fertilizer because they have nitrogen. We come to the back why to make something better? Just to produce activated carbon. Our activated carbon is a valuable material that is mostly produced from fossil sources like a coal, and they have different applications and could be like agriculture, on horticulture, gas cleaning, and removal of pollutants from the water streams like chromium or cadmium. So, however, this step is not so easy. It could not be coming directly from poultry litter to activated carbon. We need to make a pretreatment step. This pretreatment step is mostly used in the normal biomass, like a dry biomass, like a wood, making a torrefaction, because with this torrefaction, we increase the carbon content, and also to avoid possible gasification reactions during the production of the direct production of poultry litter or other biomass into activated carbon. This pretreatment that we coming from this study, or what is coming because it's coming from a research together with a university in Russia, is a wet torrefaction, because poultry litter already have around 40% water content. So it is designed currently making in Russia as sanitizing, making at the temperature of 300 degrees, a residence time of 40 minutes, a water stream flow of around 0.3 kilograms per hour, and nitrogen atmosphere. And this is mostly made for sanitizing and make a more feasible handling of this material. So we have a wet torrefaction and say, okay, so now we have a pretreatment step. So it is produced to activated carbon. So yeah, but what is the activated carbon step or treatment that we should use to produce activated carbon with these kind of applications? So the objectives of this study is the production of activated carbon from wet torrefied poultry litter through different treatments at 2 different temperatures, and the comparison of these activated carbons for the possible use in agricultural sector and the removal of pollutants. So how this study was carried out? We have a poultry litter, and we make a thermal and physical treatment in a fish-based reactor at 600 degrees and 800 degrees, reaction time of 30 minutes, and thermal by nitrogen atmosphere and physical by carbon dioxide. How is this going on? We have a preheating under nitrogen atmosphere in both cases. However, when we achieve the desired temperature, 600 to 800, in the case of physical activation, we turn to carbon dioxide, and later we make the cool down again in nitrogen atmosphere. In the case of chemical treatment, we put the biomass is coming in the batch reactor, muffle oven, and we make again a same temperature reaction time. And from previous studies from our work, and also found in the previous studies in the literature, we found that the optimum ratio is the 1:4, the char to carbon to potassium hydroxide, and again under the atmosphere of nitrogen gas. So what is the main results? So as you can see here, the activated carbons produced from physical and thermal activation, they have the higher yields, and in the case of chemical activation, we have lower yield. This is because the ash content in the case of chemical activation is 1/3, and in the case of physical and thermal is the double that the initial one, than the initial wet torrefied poultry litter. And we can assume that this change of mass, this different yield to activated carbon could be associated to the ash. So if we are making a concentration of ash in the final activated carbon, we decide to see how is the composition of this ash. So by the ICP-OS, we make analysis and we see like initially by the heating temperature, in the case of chemical activation, we decrease the content of macronutrients in the activated carbon. However, different effect is observed in the physical and thermal activation. That could be because during the chemical activation, we should wash the activated carbon after the production to remove possible hydrocyanic acid that is produced during this reaction. And in the case of micronutrients, we have similar effect. The chemical activation produces the lowest yield, the lowest content of micronutrients, and the possibility of these micronutrients is like could be used like additive. This activated carbon could be additive for use as fertilizer. In the previous case with macronutrients, it's like could be the basis of substrate for the fertilizer. So we are also interested to study the functional groups in the surface of this activated carbon. As you can see in the figure, between 3,500 to 3,200 more or less, we have the hydroxyl and carboxyl groups that is usually associated with the dehydration reaction that occurred during the thermochemical processes. In the case of carbon dioxide at 800 degrees, we can see like a small peak associated with the carbon dioxide. So we assume that this, because it's the carbon dioxide extract inside of the structure of the activated carbon during the physical activation at 800 degrees. In the wavelength of wave number between 1,700 to 1,610, we can see like the peaks associated with the carboxyl groups. And by the increasing of temperature, we decrease the intensity of these peaks, and we associated that this because of the volatilization of the organic matter that is initially in the wet torrefied poultry litter, because the wet torrefaction is, as I say, is making only at 300 degrees, so there is still some organic material in this wet torrefied poultry litter. In the wavelength of 1,560, we can see the aromatic structures, and as you probably see in the case of the carbon dioxide, we have the highest peak intensity, and with the increase of the temperature, this peak increase because we are making enhancing the polymerization reaction and aromatic reactions. And finally, in the wavelength of 1,000, we can see a peak associated with phosphorus and also with silica that is mostly obtained in the ash. And in the peak of 600 degrees is just metal halogen combination that from chlorine salts, like for example. So as I said, we have a lot of ash in our activated carbon, and we want to see what is the influence of this ash in the final pH. So for this, we take 1 gram of activated carbon, we homogenize, we dilute, we put in 20 milliliters of water, and we sex for a couple hours, and then we separate, filtrate, and figure out what is the pH of this final solution. So the ash content, we see like as you can see in the top, there is the activated carbon produced with physical and chemical activation. They have the higher pH. And in the case of chemical activation, is more in the neutral pH. This because could be, and also by the increasing of the temperature from 600 to 800 degrees, we are breaking the bonds in between the tetroatoms, like it's inside of the carbon structure. In the case we can the wet torrefied poultry litter, we have a lot of nitrogen, so this could be one of the bonds that one of the components that they are getting destroyed with interactions with during the chemical activation and physical activation. And this structure also produce like the amount of acidic functional groups decrease. And as I previously saw in the FTIR figure, we are increasing the aromaticity. So this is one of the cases why the pH is increasing with the temperature. And we also like to see how is the structure of this activated carbon. As you can see here, in general, the activated carbon produced from chemical activation have higher micro surface area, meso surface area than in the case of physical chemical activation. And one of the reasons that we assume this is because during the washing, we are again removing the ash, so the surface area is already revealed to be used as the real microporous surface area so up. In the case of physical and chemical and thermal activation, we see that in the physical activation we have higher surface area than by thermal activation, and that could be because during the using as carbon dioxide as a physical activated agent, we gasify some of the structure of the biomass, and we also making creation of new pores. But not only this, probably with the carbon dioxide, we are making cracking of volatile compounds that is deposited in the surface area, and also we are avoiding the clogging of these micropores because of the removal of the carbonous material that is deposited in the surface area of this activated carbon. And finally, briefly, what's the results about the absorption capacity? As we can see here, the chemical activation has the highest absorption capacity, and using methylene blue like indicator. And we assume that is because we have higher surface area, because in the case of methylene blue, we have to consider that by the size of this molecule, micropores could be despreciable. Also because we are increasing aromatic compounds, so there will be some interactions, and also like a low ash content will be also one of the reasons why we have higher absorption capacity with this mesosurface area. And finally, just the conclusions. The activated carbon proof the production of activated carbon by using wet torrefying poultry litter proof like it could be used like a fertilizer or additive, and also pollutant absorbent. The thermal activation have higher yields to activated carbon, but also have higher ash content, and the chemical treatment produce higher absorption capacity than physical chemicals. And this activated carbon will have some inorganic compounds like nitrogen, phosphorus, and potassium can be used like a for fertilizer production, and the most suitable in the case of absorption is 800 degrees. So thank you very much. I would like to thank this grant, and my colleagues from the University of Ghent, Przemysław Maciarka, and also Maciej Golszewski, my colleague Ekaterina Oskaniskova, because he makes the ICP measurements to determine the inorganic content, and also the student who helped us. If you are interested in more details in this study, you can consult on this published paper, and that's all. Thank you very much for your attention.
Thank you, Pablo. So we have time for questions. The first one, I think it's Shemi. Yes. Can you see it published?
Yes.
Okay.
That was question. I was you catch me now. Solution. Yeah, because we are making from the modeling from microsurface area, we are making with the Monte Carlo modeling, and in the case of mesoporous, we're making with the DFT. I think this model, I don't remember exactly the model that we use for this. So I can tell you exactly. Okay, I can find it. 1 second. Yeah, QSDTF method is cylindrical and spherical kernel. What use?
Okay.
So that's how we calculate in the mesoporous minus macro until 2 nanometers, and in 2 to 50 is okay.
Okay, so
yeah, I also sorry with the VT. Yeah, oh wait, it's because I have one range and the other range I cannot see exactly what's going on. Yes, it was making with the BT model. Sorry. Yeah.
Okay. Another question from Juan Serra. Can you see it?
We divide in two parts until 2 micrometers to calculate like a microsurface area for microporous, and over from 2 to 50 was making with mesoporous. So we divide in two parts.
Okay.
Micro and meso.
Okay. So now we have Javier Payares.
Yeah, we consider to make a Boehm tradition, and we are already trying to determine for the acidic and basic groups in the surface in the produced activated carbons for further studies.
Okay. Another one from Silvia Roman.
No, the torrefaction was made in a small. It was made at the. It's one university in Russia. Sorry for the names. Yeah, it was making by heating the water with this steam at 170 degrees, and then it was carried out with nitrogen to 300 degrees to make this torrefaction. But the amount of torrefied poultry liter, I think it was around 20 grams per batch, something like that. I don't remember exactly. And no, we didn't make bigger, longer times because we decided to make with 30 minutes. 30 minutes like the optimum to have like a short times and comparable with other ones, because otherwise with the chemical activation, the remaining structure that we will have is going to be super small. The remaining, yes, yield to activated carbon is going to be nothing.
Okay.
Because we will have like some gasification problem.
Okay. If there are no further questions, I have one. Have you said that the chemical activated carbon was washed with, it needed a washing step, no?
Yeah, we need, after the activated carbon, we wash, I can look for it if you want. Yeah, we wash with hot water, but also putting iron sulfate in the bottom of the air measure, just to ensure like we bind all the cyanidic acid.
Okay.
So we wash just with hot water around 60, 80 degrees.
Okay. This was the question. Okay. Thank you, Pablo. I think that there are no other questions, so we can go on with the last speaker. So bye, Pablo.
Bye.